When you get the chance to truly escape the glow of city lights, to find a place where you can stand under a truly dark sky, what is it that you see? You see an ocean of light. Thousands of glittering points, sharp and clear, splashed across a vast velvet blackness. It's overwhelming, and for the vast majority of human history, we looked up at that magnificent silent spectacle, and we believed that, well, that was it. We believed that this beautiful collection of stars, our home, was the entire universe. We called it the Milky Way. To us, it was everything. Scientists had a name for this concept. They called it our island universe. It was a fitting description, this idea that we were a single, populated island of light, floating alone in a cosmic ocean of infinite empty darkness. It was comfortable in a way. It was knowable. But what if that entire assumption, an assumption held for millennia, was completely wrong? What if I told you that our entire island, our vast 100,000 light-year wide home, is just a single grain of sand on a beach so vast we cannot even comprehend its edges? What if the deep, profound darkness between the stars isn't empty at all? What if it's actually filled with other islands? Not just a few, but hundreds of billions, perhaps trillions of them. Entire empires of stars, each one just as grand, just as complex, and many of them far, far larger than our own. All of them lying hidden in plain sight, mistaken for generations as just faint, fuzzy smudges of light, or perhaps distant clouds inside our own cosmic backyard. This is the story of those islands. This is the story of galaxies. They are the fundamental building blocks of the cosmos. They are violent, they are beautiful, and they are the great engines of creation. They are the stellar nurseries where stars are born, and they are the cosmic cemeteries where stars die. How did we get here? What is our future? In every conceivable way, those profound questions are tied directly to the story of galaxies. So, where do these enormous star cities come from? How do they work? What unseen cosmic forces hold them together? And what even stranger forces are slowly, relentlessly, trying to tear them apart? And perhaps the most pressing question for us, inhabitants of this particular island, what is the ultimate fate of our own home? The Milky Way. Our journey to answer these questions doesn't begin in the distant past or in the far future. It begins just 1 century ago on a quiet mountaintop near Los Angeles, where one man's patient observation would shatter our entire sense of self and rewrite our address in the cosmos forever. It's hard to overstate how comfortable, how complete our picture of the universe was just over a century ago. In the early 1920s, if you asked any leading astronomer what the universe was, they would have told you, with great confidence, that it was the Milky Way. Our galaxy contained all the stars you could see, and all the ones you couldn't. It was the beginning, the middle, and the end. Sure, there were some annoyances, some little mysteries. Astronomers had long been puzzled by these strange, faint, fuzzy patches of light in their telescopes. They called them spiral nebulae. The prevailing theory was that they were simply clouds of gas inside our own galaxy. Perhaps they were new solar systems in the process of being born, swirling into existence right here in our cosmic backyard. They were considered internal affairs, footnotes in the grand story of the Milky Way. But that all changed because of one man, Edwin Hubble, and one extraordinary new machine. In 1924, Hubble was working at the Mount Wilson Observatory near Los Angeles, using what was then the most powerful and advanced telescope on Earth, the 100-inch Hooker telescope. This giant eye gave him a view of the heavens clearer and deeper than anyone had ever had before. Night after night, he pointed this new marvel at those fuzzy, enigmatic blobs, specifically one of the most famous ones, a faint smudge in the constellation Andromeda. He wasn't just looking at it. He was meticulously photographing it, hunting for individual stars within that cloud. And he found one. But it wasn't just any star. He found a very special kind of star, a type that astronomers, thanks to the work of Henrietta Leavitt, had recently understood was a kind of cosmic yardstick. Imagine a lighthouse. You know that the lighthouse has a 10,000 watt bulb. If you're standing right next to it, it's blindingly bright. But if you see that same 10,000 watt bulb from 50 miles away, it's just a faint pinprick. Because you know its true brightness, 10,000 watts. You can look at how dim it appears and calculate exactly how far away it is. This special star Hubble found was a cosmic lighthouse. Its true brightness could be known just by observing how it flickered. So Hubble performed the calculation. He measured how dim the star appeared, compared it to its known true brightness, and did the math. The number that came back must have felt like a physical blow. The star wasn't a few thousand light years away, placing it comfortably within our galaxy. The calculation showed it was nearly 1 million light years distant. This was a distance so vast it was nonsensical at the time. It placed this star and the fuzzy cloud it lived in far, far outside the most generous estimates for the edge of the Milky Way. The implication was immediate, terrifying and exhilarating. That fuzzy smudge in Andromeda wasn't a gas cloud. It wasn't a neighbor. It was a rival. It was an entirely separate island universe, a city of stars just like our own, containing its own hundreds of billions of stars. Hubble had not just discovered a new object. He had discovered an entirely new class of object. He had proven that the Milky Way was not alone. This was the moment that triggered what astronomers call the existential shock. In a single year, our conception of reality shattered. The universe went from one knowable, cozy galaxy to a vast, dark ocean populated by, well, how many? First it was hundreds, then thousands. Then, as our telescopes got better, we realized the truth. The universe contains billions of other galaxies. This discovery redefined our place in the cosmos on the most fundamental level. We weren't just not the center of the universe. Our entire galaxy, our home of 100,000 light years and 400 billion stars, was just one speck among countless, countless others. Hubble had thrown open the gates, and in doing so, he had introduced us to the grand, chaotic, and spectacular Galactic Zoo that fills our universe. So, what exactly is a galaxy? Well, first and foremost, it's a large collection of stars, an unimaginably large collection. Your average galaxy, if there is such a thing, contains about 100 billion stars. But they are so much more than just a pile of stars. They are the true crucibles of the universe. They are the grand stellar nurseries, the only places where stars are born. Deep within them, vast clouds of cold gas and dust, so large they make our solar system look like a particle of dust, collapse under their own gravity. These are the nebulas. You may have seen pictures of them, like the famous pillars of creation within the Eagle Nebula. These are star factories, churning out new suns and new solar systems. Galaxies are also the places where stars live out their long lives and where they ultimately die, sometimes in spectacular supernova explosions that seed the galaxy with new elements. The very elements that eventually make up planets and moons and us. And the variety is stunning. It's as if the universe has an infinite artistic streak. For instance, you have the textbook beauty, the whirlpool galaxy. It's a perfect pinwheel spinning in space with two giant majestic spiral arms. You can trace those arms, glittering with 160 million stars as they curve gracefully toward a bright, dense center. Then you have something completely different like Galaxy M87. This isn't a delicate pinwheel. It's a monster. It's a giant elliptical galaxy, one of the oldest in the universe. It's just a colossal, overwhelming sphere of stars, a fuzzy, golden orb containing trillions of suns, all packed together in a chaotic, buzzing swarm. And then you have my personal favorite, the Sombrero Galaxy. It's named perfectly. It has this huge, intensely bright, glowing core, but it's sliced right through the middle by a perfectly flat, dark ring of dust, giving it the exact silhouette of a wide-brimmed hat floating in the void. They are gorgeous. They are, in some sense, the basic unit of the universe itself. But trying to understand their size is where our human minds really begin to fail. They are big on a scale that breaks our language. We measure our lives in miles and kilometers. In space, that's like trying to measure the distance from New York to Tokyo in inches. It's useless, so astronomers use the light year. It's a simple definition. The distance light, the fastest thing in the universe, travels in one single year. That distance is just under 6 trillion miles, or 9.5 trillion kilometers. Now, let's try to build a sense of scale with that new tool. Here we are, on Earth. To get to the center of our own galaxy, the Milky Way, it would take us 25,000 years traveling at the speed of light. That's just to get to the center. The entire galaxy, from one edge to the other, is over 100,000 light years across. And here's the truly humbling part. Our galaxy, this vast city of stars that takes 100,000 years to cross at light speed, is actually pretty small. It's a cosmic lightweight. Our nearest major neighbor, the Andromeda Galaxy, that fuzzy smudge Hubble first measured, is over 200,000 light years across. It's more than double our size. If the Milky Way is a large pizza, Andromeda is an industrial-sized banquet table. And even Andromeda is dwarfed. That giant golden blob, M87, is far, far bigger than Andromeda. And then there's the reigning champion, a galaxy called IC1011. This galaxy is 6 million light years across. That number is just static. Let's try this. You could take our entire Milky Way galaxy, with its hundreds of billions of stars, and lay it down. And then lay another one next to it, and another. And you would have to do that 60 times just to span the diameter of this one single colossal galaxy. So we're faced with a profound question. We know they are everywhere. We know they are beautiful. And we know they are incomprehensibly large. But why? Where did these staggering, universe-spanning structures even come from? So, where did these colossal structures come from? We know they're here now, scattered across the cosmos, but they couldn't have always existed. To find their origin, we have to rewind the clock, all the way back. 13.7 billion years ago, our universe ignited into existence in what we call the Big Bang. This wasn't an explosion in a pre-existing void, it was the sudden, rapid expansion of space itself from an infinitely hot, infinitely dense point. In that first searing hot fraction of a second, there was no matter, no stars, and certainly no galaxies. The universe was a uniform, blindingly bright soup of pure energy. Nothing like a galaxy could have survived or even formed in such an extreme environment. But the universe did two things. It expanded and it cooled. For about 200 million years after the Big Bang, the cosmos was a very different place. It was a period we call the Cosmic Dark Ages, a vast starless expanse of cooling hydrogen and helium gas. Then, the first sparks ignited in that endless darkness. Gravity, the great patient architect of the universe, had been slowly at work, pulling that gas together into denser and denser clumps. In the hearts of these clumps, the pressure became so immense that nuclear fusion switched on. The very first stars were born. These ancient suns were nothing like our own. They were giants, hundreds of times more massive, and they burned out in only a few million years. But they were the start, and once these first stars existed, gravity had something new to work with. It began to pull these pioneer stars together, forming the first small primitive groups. These were the seeds. Now, you might be thinking, that's a nice story, but how could we possibly know what happened 13 billion years ago? It's a fair question. The answer lies in one of the most beautiful facts about our universe: the speed of light. Light, as fast as it is not instantaneous. It takes time to travel. When we look at our own sun, we are seeing it as it was 8 minutes ago. When we look at the Andromeda Galaxy, we see it as it was 2.5 million years ago. This means that our telescopes are also time machines. The farther away we look in space, the further back we are looking in time, and the Hubble Space Telescope is our most powerful time machine. Astronomers pointed Hubble at a tiny, seemingly blank patch of the night sky, a spot so small it's like looking at a grain of sand held at arm's length. And they just left the telescope's shutter open for days on end, patiently gathering every last ancient photon of light from that one spot. The resulting image is one of the most profound in human history, the Hubble Deep Field. That empty patch of sky was revealed to be filled with over 3,000 galaxies. But the most distant ones, the ones whose light had travelled for over 12 billion years to reach us, they didn't look like the elegant spiral galaxies we see nearby. They looked wrong. They were small. They were faint. They were messy. They were just little, lumpy, chaotic smudges of light. These were the baby pictures of the universe. We were seeing the first infant galaxies, caught in the very act of being born, just 1 billion years after the Big Bang. This image told us the entire story. Galaxies are not born, they are built. They are assembled piece by piece over cosmic time. Our own Milky Way wasn't born as the grand spiral we see today. It began its life as perhaps a dozen or more small, irregularly shaped dwarf galaxies and lumpy structures that all formed in the same cosmic neighborhood. Then, for billions of years, gravity slowly drew them together. They collided, they merged, they tore each other apart and reformed into a larger, more chaotic mass. And as all this material, all these stars, all this gas, all this dust was pulled inward by gravity, it began to do what all things do when they are pulled together. It began to spin. You can picture it like an ice skater. When she has her arms outstretched, she spins slowly, but when she pulls her arms in, her rotation speeds up dramatically. The same thing happened to our galaxy. As gravity pulled all those smaller pieces inward, the entire mass began to spin faster and faster, and that rapid spin is what transformed the chaos into order. That lumpy, three-dimensional cloud of stars was flattened by its own rotation, collapsing down into the thin, organized, spinning disk we live in today. Those beautiful, sweeping spiral arms are just the traffic jams of this rotation, areas where gas piles up and triggers new waves of star birth. This process, this grand cosmic dance of messy mergers and rotational flattening, has happened billions and billions of times all across the universe, creating the stunning Galactic Zoo we see today. But it also left astronomers with two separate colossal mysteries. Two gigantic problems that suggested our understanding of the universe was, at best, incomplete. The first mystery was right at the heart of things. As we observed these spinning disks, it became clear that everything, billions of stars, was orbiting something, an invisible point of immense gravitational power right at the dead center. For years, scientists wondered what could be powerful enough to be the anchor for an entire galaxy. The first clues were not subtle at all. They came from deep space, from the hearts of other active galaxies. Astronomers saw things they called quasars. A quasar is one of the most violent objects in the universe. Imagine looking at a distant galaxy, and from its very center, a beam of pure energy, a cosmic blowtorch hotter and brighter than 1 trillion suns, is shooting out into space, extending for thousands of light years. This is not a subtle phenomenon, and scientists realized it was the signature of a black hole, but on a scale that is simply terrifying, a supermassive black hole. This is a black hole millions or even billions of times the mass of our sun. The quasar is the messy aftermath of its dinner. When gas, dust, and entire stars spiral into this monster, they get superheated into a glowing hot disk, and sometimes the black hole eats too fast, spitting out those enormous beams of energy. So, if these active galaxies have monsters at their core, what about our own? What about the Milky Way? Our galaxy, by comparison, is peaceful. It's quiet. There's no giant quasar beam lighting up the sky. For a long time, we didn't know if we had one. The center of our galaxy, 25,000 light years away, is hidden from our view by thick, impenetrable clouds of dust. But one astronomer, Andrea Ghez, was determined to find out. She and her team used the giant Keck telescope in Hawaii, which uses a special technology to see through that dust. And she decided to do something brilliantly simple, but incredibly patient. She decided to make a movie. For 15 years, she and her team took pictures of the stars right at the very heart of the Milky Way. Taking a picture, waiting, taking another, year after year, patiently tracking the movement of a few specific stars. When they finally played their movie, the result was breathtaking. The stars near the center weren't just gently drifting, they were whipping around an unseen point. They were being slung around at several million miles an hour, like a planet in a solar system put on a crazily fast forward. The physics was undeniable. There is only one known thing in the universe powerful enough to sling entire stars around like a rock on a string at those speeds. Ghez and her team had provided the definitive proof. There is a supermassive black hole lurking in the dark at the center of our very own galaxy. It's gigantic, about 4 million times the mass of our sun. And thankfully, it's a very long way away from us, so we are in absolutely no danger. So, mystery solved, right? This giant black hole is the invisible engine, the powerful source of gravity holding the whole galaxy together. Not even close. This is where the second and far, far bigger mystery comes in. The supermassive black hole is the local bully. It completely dominates its own tiny neighborhood, right at the very center. But it simply does not have enough gravitational pull to hold the entire 100,000 light-year-wide city of stars together. And that's the real problem. When astronomers measured the rotation of our galaxy, they found something that seemed impossible. It broke physics. Think about our solar system. It's a perfect example of how gravity works. The planets closest to the sun, like Mercury, feel the strongest gravity, so they have to move incredibly fast to stay in orbit. The planets far away, like Neptune, feel a much weaker pull, so they just crawl along at a very slow pace. This is a fundamental law. The farther you get from the central mass, the slower you move. A galaxy, which also has most of its visible mass, stars, gas, and the black hole, concentrated at the center, should follow this exact same rule. The stars on the edge, far from the center, should be moving very, very slowly, but they're not. When we measure them, the stars on the absolute outer edge of the galaxy are moving just as fast as the stars much closer in. This discovery is a complete catastrophe for physics. It's like finding that the outer horse on a spinning merry-go-round is keeping pace with the inner horse. The only way that's possible is if the outer horse is attached to a much, much stronger motor. For the galaxy, this means the stars on the edge should be flung off into the void. The fact that they aren't, the fact that the galaxy is holding together at all, means there must be an enormous amount of extra gravity that we can't see. The answer to this riddle came from a brilliant and famously cantankerous Swiss astronomer named Fritz Zwicky, way back in the 1930s. He was looking at clusters of galaxies, and he noticed the same problem. The galaxies in the cluster were moving so fast they should be flying away from each other. But they weren't. Zwicky, decades ahead of his time, said there must be some invisible stuff in between them, a huge mass that nobody could see, providing the extra gravity. He called it in German Dunkle Materie, dark matter. He was right, and he was mostly ignored for half a century. But today, we know he was right. When scientists build a virtual galaxy in a supercomputer, if they only put in the stars, gas, dust, and the black hole that we can see, the simulation fails every single time. The virtual galaxy spins itself apart. But then, they tried Zwicky's idea. They added a giant, invisible, spherical halo of this virtual dark matter, a huge scaffolding of extra gravity. And suddenly the simulation worked. The galaxy held itself together. The stars on the edge moved at the correct high speed, and the whole structure was stable. This invisible dark matter, it turns out, is the true engine of the galaxy. It is the protective framework that holds us together. In fact, we now believe it was the seed of the galaxy in the first place. That dark matter was created in the Big Bang, and it began to clump together first, and its immense gravity is what pulled in the normal gas to form the first stars and galaxies. But what is it? That is perhaps the most profound mystery in all of science. We know what it's not. It's not made of atoms, like you and me and the planets. It's some new, exotic, ghost-like particle that we haven't discovered yet. It's invisible. It doesn't glow. It doesn't reflect light. It doesn't touch anything. It's probably passing right through your body, right through the Earth itself, by the trillions every second, as if you don't even exist. And here's the most humbling part. Wait for weight. The universe has at least 6 times as much of this invisible dark matter as it does all the normal matter combined. All the stars, all the nebulas, all the planets, all of us. We are just the 15% of matter. We are just the cosmic foam on top of a deep, dark, invisible ocean. That ocean is the real master of the universe. But this discovery just opens up the next logical question. Where are they all? If the universe is filled with hundreds of billions of these galaxies, how are they arranged? Are they just scattered randomly across the void, like a handful of sand thrown across a black floor? Are they just drifting aimlessly and independently through that infinite dark ocean? The answer, as it turns out, is a profound no. There is an order to the chaos. There is a grand, overarching architecture to the cosmos. It turns out that galaxies are surprisingly social. They don't like to be alone. They gather together in neighborhoods. Our own Milky Way, for example, is part of a small, relatively cozy neighborhood that we call the local group. This group consists of us, our much larger neighbor Andromeda, and about 30 or so smaller satellite dwarf galaxies, all gravitationally bound to each other, milling about in the same general patch of space. This local group is our little galactic family, but if we zoom out, we quickly realize that our family is just one small part of a much, much larger city. Our local group is just one component of a vast cluster of galaxies. And that cluster, in turn, is just one small piece of an even more enormous supercluster of galaxies. Our full cosmic address isn't just Earth, Solar System, Milky Way. It's Milky Way, Local Group, Virgo Supercluster. For decades, this hierarchy was just a theory. But recently, astronomers decided to stop guessing and start mapping. They embarked on one of the most ambitious projects in scientific history, a cosmic census, a project called the Sloan Digital Sky Survey, built a telescope for the sole purpose of hunting galaxies. For years, it has been painstakingly measuring the exact 3D position and distance of millions of them, patiently placing one data point after another, building the first true three-dimensional map of our corner of the universe. And as this 3D map began to take shape, as the millions of points of light filled in the blankness, something profound and entirely unexpected emerged. The superclusters weren't random either. When you zoom out far enough that our entire Virgo supercluster becomes just a single bright knot, you finally see the structure, the largest structure in existence. The galaxies, the clusters, and the superclusters are all linked together. They form long, brilliant, thread-like chains that stretch for hundreds of millions of light years. These are the filaments of the universe, and connecting these filaments are the dense, busy nodes, which are the superclusters themselves. And in between these vast, interconnected threads of light are the largest things in the universe, the voids. These are immense, almost perfectly empty bubbles of darkness, hundreds of millions of light years across, where almost nothing exists. The entire universe, on its grandest scale, looks like a sponge, or perhaps, more accurately, it looks like a three-dimensional spider's web lit by faint glowing dew. This is the cosmic web. Each bright shining galaxy is just a single drop of light caught on an unimaginably long, intricate thread. And this discovery provided the final, stunning confirmation of dark matter. Because that web of galaxies, that's not the real web. We're just seeing the normal matter, the 15% of stuff that lights up. That cosmic web of galaxies is just tracing the underlying invisible scaffolding of dark matter. The dark matter formed this web first, collapsing into these long filaments and dense nodes under its own gravity after the Big Bang. And because its gravity is so powerful, all the normal gas and dust in the universe was pulled into it, like water flowing into a riverbed. The galaxies and stars we see are just the foam on top of these deep, dark, invisible cosmic rivers. So this is the big picture. This is the architecture of everything. Our entire galaxy, the Milky Way, with its hundreds of billions of stars and its 100,000 light-year span, is just one single speck of light, hidden deep inside one filament of one cluster in a cosmic web that stretches for billions of light years in every direction. It is the grandest structure we have ever discovered. And yet, this grand cosmic web, this network of filaments that lights up the universe, it looks static and permanent to our fleeting human eyes. It seems like it has been here forever, but it is not. Our galaxy, our entire universe, is a dynamic place. Its very nature is changing over cosmic time. Galaxies don't just sit still, they move, and sometimes they run into each other. In the grand scheme of the cosmos, it is a game of eat or be eaten. We can see this happening all over the universe. We can see galaxies like NGC 2207, which looks like an enormous double spiral, but is actually two galaxies caught in the middle of a titanic collision. The collision will last for millions of years, and eventually, the two will become one. Our own Milky Way is no exception to this rule. In fact, the Milky Way is a cannibal. It exists in its present form precisely because it has cannibalized, or eaten up, smaller galaxies that wandered too close. Even today, as we look out, we can see the leftovers of its most recent meals, small streams of stars that have been ripped from their home galaxies and are now being digested by our own. But that's nothing compared to what is coming. We're on a collision course, and for the Milky Way, this is bad news. Our nearest galactic neighbor, the Andromeda Galaxy, is approaching us. It is barreling towards us at the rate of about 250,000 miles per hour. The timeline is set. In about 5 to 6 billion years, it is all over for the Milky Way galaxy as we know it. Try to imagine what that would look like, standing on a future Earth. You would see the entire Andromeda Galaxy speeding towards us. No longer a faint, fuzzy smudge, it would grow to fill the sky, barreling straight into us. As the two galaxies begin to interact, they will both become more and more disturbed. The whole process starts to snowball. The two galaxies will enter what can only be described as a death dance. Computer simulations of this future crash, sped up millions of times, show a scene of both chaos and creation. As they crash together, giant clouds of gas and dust will be thrown out in all directions. The immense gravity from the merging galaxies will rip entire stars from their orbits, slinging them deep into intergalactic space. For any observer, it would be spectacular. We would have a front row seat to the destruction of our own galaxy. The two galaxies will pass right through each other. Then gravity will pull them back, and they will ultimately coalesce into one. But here is the strangest, most counterintuitive part. The stars themselves won't collide. All of the billions of stars from the Milky Way will basically just pass right by all the trillions of stars from Andromeda. The probability of one individual star hitting another individual star is basically zero. The space between them, even in a collision, is simply too vast. However, all the gas and dust between the stars, that is a different story. That will collide. As these massive clouds slam into each other at fantastic speeds, they will start to heat up. Eventually, all of this gas will ignite, and the clashing galaxies will begin to glow white hot. It is entirely possible that, at a certain point, the sky could be on fire. When the dance is finally over, the Milky Way and Andromeda, as we know them, will cease to exist. A new, combined galaxy will be born, which some have nicknamed Milkomeda. This new galaxy will be a huge elliptical galaxy, a giant, uniform ball of stars, without any of the beautiful, complex arms or spiral shape that define our home. There is no escaping what is going to happen. So what does that mean for planet Earth? The possibilities are stark. We may either be thrown out into outer space, ripped away as the arms of the Milky Way are torn apart, or we could wind up deep in the chaotic center, the stomach of this new galaxy. Stars and planets will be pushed all over the place. This may very well be the end of planet Earth. Galaxies all over the universe will continue to collide like this. But even this age of galactic cannibalism will eventually pass. Because there is an even more destructive force in the universe. A force that nothing can stop. We've discussed dark matter, the invisible glue that holds delicate structures like galaxies together. But now, scientists have found another, opposite force at work. It's called dark energy, and it has the opposite effect of dark matter. Instead of binding galaxies together, it pushes them apart. We have only discovered this in the last decade or so, but it appears to be the dominant stuff in the universe. And it is far more mysterious. We don't have the slightest idea why it's there. We don't know what it's made from. It's as if space itself has little springs in it, which are causing things to repel each other and push them apart. Far in the future, scientists think that dark energy will win the cosmic battle with dark matter, and that victory will start to drive galaxies apart. Dark energy is going to kill galaxies off. It will do this by causing all the other galaxies to recede further and further away from us. They will move away faster and faster until they are moving away from us faster than the speed of light. This means their light can never reach us again. They will become invisible. The rest of the universe will literally disappear before our very eyes. Not today, not tomorrow, but in perhaps 1 trillion years, the rest of the universe will have disappeared. Galaxies will become lonely outposts in a vast, empty, deep space. This relentless force will ultimately push everything away from everything else, stretching the universe itself until it rips itself apart. It's a distant, cold, and lonely future to contemplate. But that is not our universe. Not yet. For now, right now, the universe is thriving, and galaxies are the vibrant, dynamic engines creating the right conditions for life to exist. And that brings this entire vast cosmic story right back to us, to you, and to me. We are not just observers of this story, we are a product of it. Without galaxies, we wouldn't be here. Life itself as we know it probably wouldn't be here. We are incredibly lucky. Life has only been able to evolve on this tiny planet because our solar system was born in exactly the right part of our galaxy. It turns out, there is a galactic Goldilocks Zone, a habitable band of real estate that is, just like the story, not too hot and not too cold. It's just right. Let's imagine, for a moment, that our solar system had formed closer to the center, near that supermassive black hole. We wouldn't be here. The center of a galaxy is an extremely violent and brutal place. The stars are packed incredibly close together. Everything is moving at tremendous speeds. The entire region is flooded with so much intense high-energy radiation that life as we know it would be impossible. It would be so radioactive that the complex molecules needed to build life would be sterilized before they could even form. It is simply too chaotic, too dangerous. Okay, so what if we were on the other side of the zone? What if our solar system had formed way out on the distant, lonely rim of the galaxy? That would be just as bad. Out there, in the galactic suburbs, there just aren't as many stars. That may sound peaceful, but it means there haven't been enough generations of stars living, exploding, and dying. You need those stellar explosions, those supernovas, to forge the heavy elements, the iron, the carbon, the oxygen, the silicon. Without those, you don't have the raw materials to build rocky planets. You don't have the building blocks for water. You don't have the elements for life. So here we are. We are in the just right spot. Not too close to the violent radioactive core, and not too far out in the barren, element-poor fringes. We are in the Goldilocks Zone of the Milky Way. And this is where the story gets truly exciting. Scientists believe this habitable zone, this ring of safety and opportunity might contain millions of other stars right here in our own galaxy. And if our galaxy has a habitable zone, then other galaxies could too. The universe is immense, and the amazing thing is that we're always discovering more. We should be amazed. We are living at this specific time, a random time in the history of the universe, on a random planet, at the outskirts of a random galaxy. And yet, from this tiny outpost, we have somehow found a way to look out and understand things that stretch from the very beginning of the universe to its ultimate, distant end. We can ask these questions and we can find the answers. We are, in a very real sense, the universe's way of understanding itself. Galaxies are born, they evolve, they collide, and they die. They made us, they shape us, and our future is tied directly to theirs. We should celebrate our brief conscious moment in the sun. Have you ever truly looked up at the night sky? I mean really looked. Have you ever managed to get far away from the glow of the cities, far away from the streetlights and the headlights, and just stood there? When you do, when your eyes finally adjust to the real darkness, you see them, thousands of them, a spray of tiny, glittering lights scattered across the infinite black. It's beautiful, and it's very easy to feel small, disconnected. But what if I told you that you aren't disconnected at all? What if I told you that those lights aren't just distant decorations, but that they are, in fact, the engines that rule the entire universe? They are the reason you are here. There's a simple, profound truth that physicists and astronomers have come to understand. And it's a truth that connects you, personally, to the most distant, violent objects in the cosmos. You are made of stardust. That isn't just a poetic phrase. It is a literal, scientific fact. The very atoms that build your body, the carbon in your DNA, the oxygen you're breathing right now, the iron in your blood, every single one of them was forged long ago inside the fiery core of a star. Our destiny as a species is fundamentally linked to the destiny of stars. So, to understand ourselves, we have to understand them. And the first step is to understand the sheer, mind-bending scale of it all. When you stand out there on a perfectly clear night, in the darkest countryside, the absolute best you can hope for is to see maybe 3,000 stars with your own eyes. It feels like a lot. But those 3,000 stars are nothing. They are just the tiniest, most insignificant tip of a vast cosmic iceberg. They are just our immediate neighbors. In our galaxy alone, the Milky Way, there are over 100 billion stars. Think about that number. 100 billion. Now, hold that thought, because in the observable universe, our telescopes can see over 100 billion galaxies, each one of them a sprawling city filled with billions of its own stars. The total number is staggering. It's beyond comprehension. There are more stars in the heavens than there are specks of sand on every beach, in every desert, on the entire planet Earth. The number is so large, it feels alien. It's too much. So how do we even begin to understand what these things are? Luckily, we have a reference point. We have a Rosetta Stone that lets us decode the rest. We have one star that is incredibly close. We see it every day. We call it the sun. From our vantage point, 93 million miles away, our sun appears as a blinding ball of light, a perfect glowing disk. But if you could take away that glare, you would see it for what it is. One of the most powerful objects in our solar system, a churning, turbulent ball of superheated gas that has been lighting and warming our world for over 4.6 billion years. It dominates all life on Earth. Its sheer size is difficult to grasp, but try to picture this. You could fit 1 million planets the size of Earth inside the Sun. And yet, the humbling truth is, our Sun is tiny. Compared to the real giants out there, our star is a dwarf. Let's take a little tour of the truly big stars. We can start with a star called Eta Carinae. It's a monster, burning over 5 million times larger than our Sun, but it gets bigger, much bigger. Let's look at Betelgeuse, a famous red supergiant. Betelgeuse is 300 times larger than Eta Carinae. If you were to replace our Sun with Betelgeuse, it would swallow Mercury, Venus, Earth, and Mars without even noticing. Its fiery edge would stretch all the way out to the orbit of Jupiter. But even Betelgeuse isn't the king. That title currently belongs to a monster named VY Canis Majoris, the largest star we have ever discovered. It is, almost unbelievably, 1 billion times bigger than our Sun. These stars burn in different colors, from red to yellow to brilliant blue. Some live alone, like our Sun. Others live in pairs, orbiting each other in a complex gravitational dance. And they all come together to form those massive, sprawling cities we call galaxies. Each star is unique, a one-of-a-kind cosmic engine. But they all start life in the exact same way. They are all born from the same material, in the same place, as vast, cold clouds of dust and gas called nebulas. And when we look at them with our telescopes, we see some of the most spectacular, beautiful shapes in the universe. There's the Flame Nebula, looking like a cosmic bonfire. There's the haunting silhouette of the Horsehead Nebula, and the vast, complex clouds of the Orion Nebula. Each one of these is a star nursery, a place where millions of new stars are currently being born. But for a long time, the birth itself was a complete mystery. You see, when we looked at these nebulas with normal telescopes, the most dramatic parts weren't always the beautiful glowing gas. The real secret was hidden in the dark parts. These dark patches are areas of incredibly dense gas and dust, so thick that regular light cannot get through, and that's where the real action is happening. For decades, we could only guess. We knew stars were being born in there, but we couldn't observe them. We could not see the first moments of a star's life at all. Imagine that. The most important objects in the universe, the very things that make our existence possible, and their birth was completely hidden from us. That all changed in 2004, when NASA launched the Spitzer Space Telescope. Spitzer was a different kind of eye. It wasn't designed to see visible light the way we do. It was an infrared telescope, which means it was designed to see one thing: heat. And unlike light, heat can pass right through those thick, dark clouds of dust. When Spitzer turned its eye to those dark patches, areas that were entirely dark to our old telescopes suddenly became bright. For the first time, we could peer inside the nursery. We could finally see the very earliest parts of star formation, witnessing baby stars coming to life. And what we learned is that the recipe for a star is actually remarkably simple. All you need to make one is just 3 ingredients: hydrogen, gravity, and time. It all starts with gravity. Gravity is the sculptor. It begins to pull these vast, cold clouds of dust and gas together. It gathers them into a giant, swirling vortex. Now, when you bring matter together, a simple law of physics kicks in. When you squeeze things into smaller spaces, they necessarily heat up. It's the same reason your bike pump gets warm when you use it. You compress something, you drive the temperature up. Over hundreds of thousands of years, gravity continues to pull, and the cloud gets thicker and hotter as it forms a giant spinning disk, a disk that is often bigger than our entire solar system. At the very center of this disk, gravity is relentless. It crushes the gas into a super dense, super hot ball. This is the embryo of a star. But this birth is not a gentle or peaceful event. It is incredibly violent. As the pressure at the center builds, it becomes so intense that huge jets of gas burst out from the core, shooting material away in opposite directions. These jets are enormous, stretching for many light years across space. It shows you just how violent this process is. Something is accelerating material at incredible speeds across unimaginable distances. All the while, gravity keeps the pressure on. It keeps sucking in more gas and dust particles, which smash into each other, generating more and more heat. Over the next 500,000 years, this young star gets smaller, brighter, and hotter. The pressure builds, and the temperature at its core continues to climb until it finally reaches the magic number, 15 million degrees. Only at that mind-boggling temperature, a temperature so hot it's almost impossible to imagine, can the atoms of hydrogen gas finally overcome their natural repulsion and begin to fuse together. That fusion releases a massive, sustained burst of energy, and just like that, the furnace is lit. A star is born. It will now shine for millions, perhaps billions, or in some cases, even trillions of years. Our own sun has been doing it for 4.6 billion years already. What kind of fuel could possibly last that long? If the sun were made of coal or wood, it would have burned out in a few thousand years. If it were powered by the chemical reactions that fuel our rockets, it would be gone in a geological blink. This was the single greatest problem facing physics at the turn of the last century. We looked up every day at this colossal engine, and we had no idea how it worked. We needed a new engine, a fabulous source of energy, and the answer came from the mind of a genius, Albert Einstein. The secret of the stars, the source of all their light and heat, is captured in the most famous equation in history. E equals mc squared. We've all seen it, but what does it truly mean? It means that energy, E, equals mass, m times the speed of light squared, c squared. The c squared part is just a giant number, which tells you that a tiny amount of mass is equivalent to a staggering amount of energy. In essence, what Einstein revealed is that matter itself, the stuff you're made of, the chair you're sitting on, the air you're breathing, is concentrated, condensed energy. It's frozen energy, and it's possible to release it. The process by which stars do this is called nuclear fusion. They are, quite literally, smashing atoms together. Inside that 15 million degree core, the star's main fuel, hydrogen, is under unimaginable pressure. Now normally, hydrogen atoms, which are basically just protons, would repel each other. They have the same positive charge, and just like trying to push the north poles of two magnets together, they desperately want to stay apart. But inside the star's core, the heat and pressure are so intense that these hydrogen atoms are moving at incredible speeds. Heat is just motion, and they are moving so fast in such a confined space that they can't avoid smashing into each other. They overcome that repulsive force and fuse. When they do, they create a new element, helium. But here is the real magic, the secret to the whole thing. If you could somehow take the hydrogen atoms that go into the reaction and put them on a scale, and then take the helium atom that comes out and put it on another scale, you would find something amazing. The helium weighs slightly less than the hydrogen that went into making it. A tiny fraction of the mass has vanished, but it hasn't really vanished. That missing mass has been converted directly into a pure, massive blast of energy. That is E equals mc squared in action. That tiny bit of lost mass, multiplied by the speed of light squared, is what we see as sunlight. It's the heat we feel on our skin. This isn't just a theory. We are so confident this is how it works that we are actively trying to build our own star right here on Earth. Inside a laboratory near Oxford, England, there's an 80,000-pound machine called a tokamak. You can think of it as a large magnetic bottle, a cage designed to hold a superhot plasma and recreate the conditions inside a star. Every day, scientists there heat hydrogen gas to more than 300 million degrees. That's many times hotter than the sun's core. They have to do this because they can't duplicate the other key ingredient of a star, the truly insane pressure. But by reaching these temperatures, they can force the hydrogen atoms to fuse into helium and release that burst of energy. The catch: the tokamak can only maintain this fusion reaction for a fraction of a second. A real star does it for billions of years. The reason is simple: size. The true engine that drives a star is gravity. Stars are huge. You need that immense amount of gravity, all that mass crushing inward, to compress the star's core and create the fantastic amounts of heat needed to ignite nuclear fusion naturally and, more importantly, to sustain it. This leads to the central beautiful concept of a star's entire life. A star, as Dr. Michio Kaku says, is a gigantic hydrogen bomb. It's constantly trying to explode. So why doesn't it? Why does it just sit there, shining peacefully? It's because gravity is compressing the outer layers of the star, pushing inward. What you are seeing when you look at a star is a perfect, epic battle. It is a constant tension between two of the most awesome forces in nature. In the core, the fusion process is releasing unimaginable energy, creating a massive outward pressure that wants to blow the star apart. At the same time, the star's own colossal gravity is trying to do the exact opposite. It is crushing inward, trying to collapse the star down to smithereens. A star is this balancing act. It is this dynamic standoff, frozen in time. That tension, that perfect equilibrium between the outward explosion and the inward collapse, is what creates the star. And the energy it releases, that missing mass from the core, is what we see as starlight. This light travels across the vacuum of space at the ultimate speed limit, 670 million miles an hour. Nothing moves faster. And yet, the universe is so incomprehensibly vast that the light from most stars takes hundreds, thousands, or even millions of years to reach us. The light we see today from the giant star Eta Carinae left that star 8,000 years ago, around the time our ancestors were first figuring out agriculture. The light from Betelgeuse has been traveling since Columbus sailed for the Americas 500 years ago. When we look up at the night sky, we are not just looking across space. We are, quite literally, looking back in time. But that journey of thousands of years through space is only the final leg of the trip. Before that particle of light, that photon, even begins its journey to us, it has to first escape the star it was born in. And that is an odyssey all on its own. When a photon is created in the 15 million degree core, it doesn't just fly straight out. It's born into one of the densest places in the solar system. There is an entire star in its way. The moment that photon is created, it travels an impossibly small distance before it immediately slams into another atom. It gets absorbed, and then, a split second later, it's shot off again. but in a completely random new direction. It might go up, down, left, sideways. It might even go backwards, deeper into the core. It's engaged in a kind of cosmic drunk walk, bouncing billions upon billions of times, being absorbed and re-emitted, slowly, randomly, struggling to work its way out. It's almost comical. A particle of light, the fastest thing in existence, is trapped. That single photon takes, on average, thousands and thousands of years just to get from the core of the sun to its surface. And then, once it finally breaks free, it's only an 8-minute trip from there to here. All of that energy, from countless photons pushing their way out, has a profound effect on the star itself. It's not just light and heat, it creates something far more destructive. As all those photons finally reach the surface, they heat up the outer layers of the star, sending the gas churning and boiling in a state of extreme, violent turbulence. Our sun's surface is not a calm, placid ocean of fire. It is a roiling, chaotic storm. In fact, it's so violent that, thanks to orbiting satellites like SOHO, we can actually hear it. The sound of the sun, sped up to be audible to our ears, isn't a gentle hum. It's a deep, powerful, thundering roar. This chaos of speeding, superheated gas, which we call plasma, does something else. It generates powerful, intense magnetic fields. As the star rotates, these fields get stretched, twisted, and tangled up like cosmic rubber bands. Eventually, they get tangled so badly that they snap and burst through the surface. When they do, they create giant magnetic loops, spectacular arches of glowing plasma that erupt into space. Some of these loops are so massive that the entire planet Earth could pass right through the middle of one, with thousands of miles to spare on every side. They are beautiful and they are deadly. Scientists at Caltech managed to recreate a version of this right here in a lab. They created 2 of these plasma loops and watched what happened when they clashed. They found that when these loops collide, they trigger a massive, explosive burst of energy. On the surface of a star, that's exactly what happens. These giant loops smash into each other, and the energy released sends temperatures in that one spot soaring from a mere 10,000 degrees to over 10 million degrees in an instant. That extreme sudden heat is the trigger for the solar wind. It's a blast that sends millions of tons of electrical particles streaming away from the star at over 1 million miles an hour. This isn't a wind like we have on Earth. It's a constant stream of high-energy particles that can damage our satellites, disrupt communications, and even put astronauts' lives in jeopardy. That's the wind from our tiny sun. If we were unlucky enough to be orbiting a giant star like Eta Carinae, the story would be very different. The wind from that monster would be so powerful, its energy so intense, that it would be hell on Earth, quite literally. It would strip away our atmosphere, boil our oceans, and melt the very surface of the planet. This is the true, destructive fury of a star. Understanding how these forces work can help us protect ourselves, to predict their most violent outbursts. But there is nothing we can do to protect ourselves from the single, most destructive event of all. The moment when a star finally, inevitably, dies. That perfect billion-year balance between gravity and fusion is a beautiful thing. But it is a temporary truce, not a permanent peace. It cannot last forever. From the very moment it is born, every single star, from the smallest dwarf to the largest giant, is destined to die. Its fuel will eventually run out. And on that day, that epic battle ends. The outward push of fusion ceases, and gravity, the relentless, patient force that has been crushing inward for billions of years, finally wins. Our own sun is no exception. It is middle-aged, steadily burning through its fuel supply. Every single second, it converts 600 million tons of its hydrogen fuel into helium and energy. At that incredible burn rate, it has enough fuel to keep shining just as it does now for about another 7 billion years. It seems like an eternity. But in cosmic terms, the clock is ticking. And when that fuel in the core finally begins to run low, the end begins. The fusion process, the outward explosion that has held gravity at bay for 10 billion years, begins to sputter and slow down. This gives gravity the edge. With less force pushing outward, gravity begins to win the tug of war, and it compresses the star's core. But this crushing act of desperation doesn't kill the star, not yet. Instead, it acts as a bizarre second wind. The compression heats the core even further, to the point where it ignites the remaining shell of hydrogen gas around the core. This new frantic burning heats the star's outer layers to incredible temperatures. And when you heat up a gas, it expands. And so, our sun will begin to swell up. This isn't a sudden event. It's a slow, horrifying transformation over thousands of years. It will expand far beyond its current size, growing from a familiar million-mile-wide star to a bloated, monstrous one, over 100 million miles across. Our sun will become a red giant. It's difficult, perhaps impossible, to truly imagine what that day will look like for any descendants of Earth. Imagine a sunrise 7 billion years from now. You wouldn't see a small, cheerful, yellow disk rising peacefully. What you would see is a huge, swollen, bloated red disk, slowly, terrifyingly, reaching up over the horizon. It would look less like a sun and more like a wound in the sky. When this red giant sun is fully up, it will dominate the sky, stretching from one horizon to the other, and it will be blasting down unimaginable heat upon the Earth. The effect would be catastrophic. Scientist Phil Plait describes it as being like sticking your head in an oven and setting it to broil. The temperatures here on the surface will reach thousands of degrees. The oceans will be the first to go, boiling away into a thick, scalding steam that the new, stronger solar wind will strip from the planet. The atmosphere itself will be next, seared away into space. Finally, the rock itself will yield, the mountains will melt, and the entire surface of the Earth will become a sea of molten lava. The bloated star will then continue to expand until it simply engulfs our planet, swallowing our world whole. But this giant red star is dangerously unstable. It is, in fact, destroying itself from the inside out. With no hydrogen left in its exhausted core, it will begin burning its backup fuel, helium, fusing it into carbon. This new fusion is violent and unpredictable. It blasts furious, convulsive surges of energy from its core to its surface. These energy waves, these thermal pulses, become so powerful that they will, over time, gently but relentlessly blow away the star's outer layers. It's as if the star is exhaling, puffing away its own substance in giant cosmic smoke rings. Slowly, layer by layer, the star disintegrates, its gases drifting away into the darkness. The red giant is dead. And what's left behind? After the beautiful glowing shroud of its outer layers has drifted away to form a nebula, all that remains is the intensely hot, impossibly dense core. The red giant has become a white dwarf. The fusion process has finally truly stopped. The engine has come to rest. This stellar remnant, this corpse, will be no larger than the planet Earth, but it is 1,000,000 times denser. A white dwarf is a truly amazing object, a place where the laws of physics are pushed to their limit. It's so incredibly dense that if you could somehow take a single sugar cube-sized chunk of its material and place it on the surface of the Earth, it would be so heavy, so dense, that it would fall right through the ground, pulled down by gravity as if the planet's crust wasn't even there. And at the very heart of this white dwarf, astronomers believe there is a giant crystal of pure carbon, a cosmic diamond thousands of miles across, a trillion carat diamond, the final beautiful jewel of our sun, left floating silently in the sky. This is the fate of our sun. It's a relatively quiet, almost graceful end, but this isn't what happens to all stars. When stars that are much bigger than our sun die, their death is not gentle at all. It is spectacularly, unimaginably violent. And in that violence, they create something far more precious than a massive diamond. They create the very building blocks of life itself. Giant stars live fast, burn bright, and die hard. Let's take our old friend, Betelgeuse, that red supergiant that's 20 times more massive than our sun. Because it's so massive, its gravity is overwhelming. This creates pressures and temperatures in its core far greater than anything our sun could ever achieve. Its core isn't just a simple furnace, it's a high production factory. It doesn't just fuse hydrogen into helium. When it runs out of hydrogen, which it does in only a few million years, it immediately begins fusing helium into carbon. Then, in a frantic race against gravity, it fuses carbon into oxygen, then oxygen into neon, then neon into silicon. The star's core becomes structured like an onion, with a shell of hydrogen fusing at the very outside, then a shell of helium, then carbon, then oxygen, all surrounding a growing core of the final, heaviest elements. This factory line is also what leads to the star's destruction, because eventually, after all those other stages, it fuses silicon, and it creates the element iron. To a massive star, iron is the most dangerous element in the universe. It is poison. It is the end of the line. Here's why. All the other elements, when they fuse, release energy. They create heat. That's the outward pressure that holds the star up against gravity. Iron is different. Iron absorbs energy. It does not release it. When the star's core becomes a solid, growing ball of iron, the furnace goes out. The star is now desperately trying to dump energy into that iron ball, trying to make it fuse into something heavier, but it can't. That iron core is robbing the star of the very energy that was supporting it. The star has just written its own death sentence. The epic, billion-year battle between gravity and fusion is over, and gravity always wins. From the moment a massive star begins to create iron in its core, it has only seconds to live. With no outward fusion pressure, the star's iron core, a ball the size of Earth but with more mass than our sun, has nothing to support it. It collapses instantly. It doesn't just fall, it slams inward upon itself at nearly a quarter of the speed of light. In less than a second, the core is crushed down to an object the size of a city. The outer layers of the star, billions of miles of gas, an incomprehensible amount of mass, are suddenly left hanging in the void with nothing supporting them. They pause for a split second, and then they too begin a catastrophic freefall, slamming down onto the new, super-dense core. This collision creates a huge, catastrophic shockwave that rebounds outward, and the star literally tears itself apart in the single most violent event in the universe, a supernova. In just those few seconds, that single explosion creates more energy than our sun will produce in its entire 10 billion year lifespan. It's an explosion so bright that for a few weeks, it will outshine its entire home galaxy of 100 billion other stars. It's almost funny to think about. The next time you're cooking and you pick up a heavy cast iron frying pan, just remember, the iron in that pan, or iron just like it, killed a star. And it did it in just a few seconds. We scientists used to believe that in a supernova, the star literally blew itself to bits, and that there would be nothing left. We were wrong. There is a corpse left behind. After the smoke clears from this cosmic detonation, the super-dense core that survived the blast remains. It is some of the most exotic matter known to science, a neutron star. This object is tiny, perhaps only 20 miles across, the size of a single city. But it is unbelievably heavy. That sugar cube analogy we use for the white dwarf. It's not nearly good enough. Gravity has crushed this core so completely that it has squeezed protons and electrons together to form a solid ball of neutrons. A single sugar cube-sized chunk of this neutron star material would weigh 1 billion tons, as much as all the cars in the entire United States combined. But this bizarre city-sized object isn't the only thing the star leaves behind. In that final, violent explosion, it blasts all those new factory-made elements, the carbon, the oxygen, the silicon, the iron, far out into space. Scientists who have simulated these explosions in labs have found that when these stars explode, they almost turn inside out. The material from deep within the star's core, all those newly forged elements, actually surfs the shockwave. It rides that colossal wave of energy, trading places with the outer layers, and is blasted clear out into space. And in the extreme, unimaginable heat and turmoil of that explosion, a final, frantic alchemy takes place. The pressures and temperatures are so high in those few seconds that even the iron core is broken apart and fused into elements that are heavier than iron. This is the one and only place in the universe where the heaviest elements are forged. All the gold in your wedding ring, all the silver in your coins, all the platinum in our electronics. None of it can be made in a normal star. It can only be created in the dying, explosive breath of a supernova. And because there's so little time for these elements to form before the explosion rips everything apart, they are the rarest and most valuable materials in the cosmos. But the most important legacy isn't the gold. It's everything else. The dying star doesn't just leave a neutron star behind, it seeds the universe. It blasts those new elements, all the products of its billion-year life and its fiery 2-second death, far out into space. This cloud of debris, this stardust, is enriched with hydrogen, carbon, oxygen, silicon, iron, and yes, traces of gold and silver. This cloud, the ghost of a star, is the raw material to build new stars, new solar systems, new planets, and of course, us. This is the very heart of our story. This is the profound connection. When we say you are stardust, it is not poetry. It is physics. Look at your hand. The atoms in your left hand may have come from a completely different star than the atoms in your right hand. You are quite literally a star child. Every single atom in your body, other than the most basic hydrogen, was produced inside the fiery core of a star that lived, died, and exploded billions of years ago. The carbon that forms the basis of your DNA, the oxygen you need to breathe, the iron in your blood that carries that oxygen to your cells. All of those things had to be generated inside the belly of a star. There is simply no other way to get them. Everything we see around us, the ground beneath our feet, the air we breathe, our own bodies, it all was once blasted out from the core of a star. In fact, even the atoms in our own sun are recycled. Our star is a 3rd or 4th generation star, formed from the debris of even older stars that died long ago. This leads to a beautiful, almost poignant realization. Our sun is our stepmother. It gives us warmth, it gives us light, and it nurtures our world. But our true mother was a massive, anonymous star that died in a catastrophic supernova explosion billions of years ago. It died to give birth to the elements that would one day clump together to form our solar system, our planet, and our bodies. It's a beautiful thought, this endless cycle of death and rebirth. Stars die, they seed the universe with the raw materials for life, and new stars and new planets are born from that debris. But this cycle, too, must eventually come to an end. We are living, right now, in the great age of stars, but it is a temporary age. The universe, vast as it is, only has a finite, limited supply of hydrogen, the primary fuel for every star. And trillions upon trillions of years from now, it will all be used up. When there is no hydrogen left, the great star nurseries will go cold and dark. There will be no new stars. And the existing lights in the sky, the ones that have defined the universe for so long, will, slowly and inexorably, begin to blink out. The first to go will be the massive, brilliant blue giants, which live fast and die young. Then, the mid-sized yellow stars, like our own sun, will burn through their fuel, puff off their outer layers, and fade into cold, dead white dwarfs. For trillions of years after that, the universe will be lit only by the dim, faint, rusty red glow of the smallest, longest-lived red dwarfs. But even they cannot burn forever. Eventually they too will fade away. The universe will get colder and darker until the last star finally burns out and the universe becomes dark once again. The age of stars will be over. That future sounds grim. It sounds dark and cold and empty. But you can, and I think you should, take something profoundly positive from that. The very fact that this age will end is exactly what makes this moment, right now, so incredibly precious. We are not living in the cold, dark beginning of the universe, nor are we living in its cold, dark end. We are alive in the brief shining window in between. We are here during the time when the skies are illuminated, when stars are still being born, and when those stars are actively creating and spreading the elements necessary for life. This is the best time to be alive. We are, right now, living in the golden age of the universe. We are living in what you might call the season for life, a specific period in the universe's long history that lasts for a few billion years. Knowing this, at least for me, makes me appreciate the way things are right now, because they weren't always this way, and they won't always be. We live in the best of all stages of the universe's evolution. For now, the stars will continue their work. They will keep shaping our universe, generating the building blocks for new worlds and creating new stars. And for now, they will continue filling the darkness with light. The next time you look up at that spray of glittering lights, remember what you are. Remember that you are the universe's way of understanding itself. You are stardust, alive and awake in the golden age.